Good afternoon, everybody. My name is Adrian Suksmono from ITB, and today I give a lecture on the introduction of ground penetrating radar and a little bit about subsurface imaging. So the agenda for today's lecture will be consist of six topics. In the first part, I will talk about the concept of GPR. What is GPR? In second one, I will describe the principle of ground penetrating radar. In the third part will be discuss about the pulse ground penetrating radar. And in the fourth part, especially with the continuous wave ground penetrating radar, which consisting of three subtopics. In the first subtopics, I will talk about step frequency radar. Second one, frequency modulated radar, and I will give an example of modular FMCW radar. Actually, this radar is built by ITP, by our team, and we open the design. So basically, everybody can replicate this radar for further investigation. In the fifth part, I will describe a bit about the GPR application and data interpretation. And in the last part, I will introduce the subsurface imaging. Sorry, this. Especially the magnetic field camera or the B camera. Next. So we come to the first topic about what is GPR. Well, people are fascinated to see hidden objects. So, for example, if you like to read comic book, you know that Superman have a special ability. He can see through a wall and identify if there are victims inside a room that anybody else cannot see, or some terrorists inside the rooms. So of course, if we have such capability, we will be very, very happy. But some people will be very unhappy because we can now see everything that should have been hidden. And for some purpose, for example, if we want to look for treasures that are buried under the ground, it will be very helpful if we have a device that can see through the ground and find these objects. So similarly, if we have a buried archaeological site or room that buried under the ground, we can find it. If we can see through the ground, then it would be very helpful to find such room. And for the last one, sometimes people have to face with some difficulty after the war. There are so many landmines which are buried, and sometimes there are some accident that it will be exploded and hurt people. So if we can find this buried object, buried landmines, then it will be very, very helpful for us to have such a device. So in general, GPR, what is GPR? GPR is a ground penetrating radar. So basically it is a radar, radio detection and ranging device. So an equipment, a device which uses radio wave for sensing and detection, and find the range, the distance between the objects we want to find and the antenna. Yeah. And secondly, because it is named as ground penetrating, it's capable to penetrate the ground. But as we see later, this penetrating capability is limited by some factor. For example, it is limited by the frequency that we use. So for higher frequency, the penetrability will be reduced and if we use low frequency, then it can penetrate more. But we have to pay the resolution of the object that we want to detect. Next. Okay, before going through the detail, we can see here some uses of GPR. So GPR normally can be used by archaeological person to do the survey. So for example, in an area, we suspect that this area long time ago, there are cities, there are caves or other human-made objects, but now we cannot see it because it is already buried underground. So we can use the GPR to figure out how big these objects are. And in modern usage, we can use it for concrete inspection. So in a building, for example, if we are by an old building and we want to see whether the construction is still usable or whether it is already weak, then we can use the radar to find out and to estimate the strength of the building. Also, we can use it for utility scan. For example, if a telecom operator want to bury their cables or power electricity want to bury their cables, they have to dig the road. But sometimes there are accidents, they cut existing facilities. So in this case, the GPR will be very useful because we can find if there are pipes or cable under the ground, and we can avoid such accidents. And the last example is for bridge inspection. So sometimes if you go to from Bandung to Jakarta using highways, we have a very long bridge, and sometimes this bridge damage, because the traffic is heavy, because it rains every day. And by using GPR, we can figure out how much damage already made by the usage of this bridge, and we can fix it. We can find which part that has to be fixed. So these are the example of GPR usage. Next. Well, before go to the special construction of the GPR, we will see other uses of GPR. So we have two kind of usage. In the right part, there's a police officer that used the radar to see through wall, through the wall. So he now have a capability almost like a Superman. So if there are terrorists, there are enemies inside the building, and it is hidden, it is obstructed by walls, the policeman, the army can see through the wall by using this through wall radar, which in principle it is ground penetrating radar operated in a different mode. And sometimes we can use such kind of radar in borehole imaging. So in borehole imaging, we use the radar, the antenna, transmit and receive antenna will be separated, and we dig under the ground and we do the imaging. And you can see here it is a little bit different with the normal radar, because instead of sensing the reflection, direct reflection, it is now it is transmitted through the objects. And furthermore, there are other similar imaging modalities, but with using different waves. For example, in the hospital, we can find computerized tomography. The computerized tomography can see through the body of patients, and it uses X-ray or gamma ray, which is actually also electromagnetic wave with extremely high frequency. Also, we can see in the hospital, they have ultrasound imaging system, USG, and sometimes we can inspect it. We can be inspected by doctor to see whether there are cancer inside our body. And this kind of imaging uses different wave. In this case, it's ultrasound. So it is a sonic wave. It is a sound with extremely high frequency. And we can also see in the hospital, they have MRI, magnetic resonant imaging. And this is a very different kind of imaging, although the detected wave is also a radio wave, but actually the wave comes from the nuclear of an atom inside the patient. And next, we can see the seismic imaging that used by seismic surveyor. So to see the structure of layers under the ground, to find mineral, to find oil, we can use seismic imaging. And the seismic wave is also a little bit different with other waves. So instead of sound, they use dynamite or hammer, sometimes hammer. Then we have receiver, which is constructed as an array. Then based on the receiving signal, we can infer what kind of structure under the ground. And the last one is a magnetic field imaging, which I will discuss in the last part of this lecture. Now we come to the second part, how GPR works. So this is the basic principle of the GPR. So in the GPR, basically we transmit a pulse of electromagnetic wave, such as in a normal radar, and then we capture it. What makes it different is that normally the GPR is operated in a short range. That means that we want a high resolution image, which implies later you can see that we have to transmit an ultra wideband pulse, ultra wideband electromagnetic waves. So in time domain, it looks like a monocycle. So it is something like a sinusoid, but it is only one cycle. And then after sending this monocycle, the receiver will detect where actually will do the sampling and then recording it in a digital format. So in the middle part of this picture, you can see a typical pulse, typical signal that we call it the A scan, So this is the scan, one-point scan by the radar. And the rank of this A scan, a P scan. The P scan is obtained when we move around the GPR while doing the scanning. So for a point object, what we have in the screen is not a point. Why? Because the antenna did not only receive a direct reflection from the object, but it also received from another angle. Yeah. So we can prove that the form of the reflection is hyperbole. Next. There are important parameters that we should know when we deal with the GPR. So we have to know the frequency, the working frequency, the resolution or the bandwidth, and also the pulse repetition frequency. So first we see the right part of this figure. This is the spectrum, the electromagnetic spectrum. Our eyes can see only the light wave, and this is displayed as a rainbow, in this right part. And this light wave have 700 nanometer up to 400 nanometer wavelength. And the GPR works in the left part of the spectrum, which is typically several megahertz up to several gigahertz. So it is depending on the purpose. So for example, you want to find the source of water under the ground, you have to use something like 10 or 20 or 50 megahertz. But if you want to inspect the concrete or the construction of a building to find out how the repair already correct or not, then you have to use a higher frequency of several gigahertz. And this frequency affect the penetrability of the radar. As I talked previously, if you use low frequency radar, low frequency means that the center of the radar is the center of the working frequency of radar, several megahertz, then you can penetrate quite deep under the ground. But if you use high frequency, then only a few centimeters, you can see only a few centimeters. Why you can open again your electromagnetic or field course. There is a relationship between the skin depth and the frequency of electromagnetic. And the second part is the resolution, which is directly connected to the bandwidth of the radar. So we want the bandwidth. Normally, if you have a large bandwidth, then you have to pay more. So the radar becomes expensive. The reason is if you have a large bandwidth, then you can get a better resolution. And we have an equation that states this condition. If we say that if we notate the resolution by delta R, then it will be equal to C divided by 2 multiplied by the bandwidth. So C, where C here is the speed of electromagnetic wave, the speed of light. It is about 300 million meter per second. So in this case, if you know the bandwidth, but in the pulse radar, you will be informed the pulse width. Pulse width will be denoted by delta T, and the relationship with the resolution is delta R will be equal C multiplied by delta T. Sorry, it should be divided by 2. So C is the speed of light. And the last important parameter is pulse repetition frequency. And it determines the maximum ambiguous range. So we denote the range with RU max. And this is the spec of the radar. So you can work with object that is beyond the RU max. And here we have an example, a small example, how to calculate this parameter. So for example, you buy a radar. It is written here that it is written in the spec that the PRF is 100 kilohertz. The frequency spans from 1 giga to 4 gigahertz. And suppose that the C is 300 million meter per second, then you can calculate the center will be 1 plus 4 divided by 2. It is equal to 2.5 gigahertz. The bandwidth will be 4 minus 1, which is 3 gigahertz. And the resolution, your expected resolution will be C divided by 2 bandwidth. And if you put every number in it, then you will get about 5 centimeters. And finally, the RU max will be C divided by 2 PRF, and will be 1.5 kilometer, 1,500 meters. So in principle, we have two kinds of radar that we call here the pulse and the continuous wave radar. In the pulse radar, whether it is a normal radar or a ground penetrating radar, we transmit the pulse of electromagnetic energy and then wait until an object reflects the wave, and we get the echo. The echo will be received by the receiver, and it is demodulated and they sample, and then we get reflection, a characteristic or a range signal that indicates where the objects come from. And if the radar quite advanced, you can also get how fast the object move by Doppler processing. And in the right part, I figure out you can see the image of a continuous wave radar. So instead of pulse, this radar continuously transmit electromagnetic wave in a particular pattern. And the simplest one is the linear modulated frequency, linear frequency modulated wave. Now we come to the third part. We'll explain a little bit about the pulse radar. So I already explained previously about the pulse radar. So in principle, we transmit a pulse. We transmit a pulse periodically, and then the receiver will receive the reflected wave and do the sampling. And GPR, current day GPR, works on using digital signal processing. So after getting the digital samples, we can do several processing steps, and we get the image. In the right part, you can see example of radar, and I think this kind of radar is produced by Mala Geoscience. It is a small radar manufacturer, but it is widely used in the world. And the boxes are antennas of the radar. So in the bottom part, you see large box correspond to a large antenna, and it means that we use this antenna with center frequency quite low center frequency. But in the top part, you see smaller boxes. Smaller boxes means that we work in higher frequency. So let's go to discuss about the continuous wave GPR. The first one is step frequency continuous wave radar. Well, in the pulse radar, it is said that we work in time domain. In time domain means that we transmit pulse and receive, and then measure the time difference between the transmitted and received wave or received pulse. And from that time delay, we can calculate easily the distance between the radar and the object we want to detect. In the continuous wave radar, whether it is step frequency or frequency linearly modulated frequency radar, we work in frequency domain, which means that we scan the object with the electromagnetic wave that subsequently increase frequency. So for example, we start with F0, let's say it is 1 megahertz, then we transmit the wave, and then receive the wave, doing the demodulation, and then measure the signal, the voltage in the demodulator. And normally we have a pair of values. The first one is in-phase values, and the second one is quadrature. And we combine these values into one, and we can get the Fourier coefficient for F0. And then after getting this data, we transmit again F1, for example, 2 megahertz, and etc., 3 megahertz, etc., until the final Fn, n megahertz. And after collecting all of this Fourier coefficient, you do the inverse Fourier transform. After inverse Fourier transform, what we get is a range signal displayed in the right part of this image. So in the right part, you see two peaks in the middle part of the image. It indicates that there are two objects in the range about 40 and 70 something unit time or unit distance, meter, for example. And the center part, maybe you are familiar that it looks like spectrum, and it is actually a spectrum that we obtain because of the Fourier transform we do in the signal processing. Okay, this is the basic construction of step frequency radar. And in the left part is the ordinary, in the right part is compressive sensing, GPR. Maybe I will introduce a bit about compressive sampling radar later. We see now the left part. So basically, you can see in the left part of this figure, there is a step, yeah, step. So a curve of steps. The horizontal axis indicates the time, and the vertical axis indicates the frequency. So this means that for a particular delta t time, we transmit a frequency monotone, monotone frequency of electromagnetic wave, and then it is increased by discretely into the second frequency, etc. So in this case, we have to have inside the radar, we have frequency synthesizer. And after generating this monotone, then we transmit it by using transmit antennas and receive it by using receive antenna. And in the receiver, we do quadrature mixing. After quadrature mixing, we get two kind of signal, I and Q, which means that I is in phase signal, Q is quadrature signal, and after it is actually still an analog signal, so we have to apply the AD conversion, and then it is converted into digital signal. So when we use the ordinary step frequency radar, what we do is just doing the inverse Fourier transform, and that's all. We get the range signal. But in the step frequency, in the compressive sensing GPR, we have to construct the signal using optimization algorithm. And so what is the usage of this compressive GPR? So you see that normally to scan a number of frequencies, for example, 1,000 frequencies, it takes time. So for example, 1 second, 2 seconds, etc., it takes a long time. But by using compressive sampling radar, you can reduce the time by sampling only a particular frequencies. But we have to pay by the reconstruction complexity. You have to employ a good computer, a good algorithm to get a better result. And yes, this is the realization of the radar. It is both the step frequency and compressive sampling step frequency radar. We built this radar several years ago, maybe 15 years ago, and it is a cooperation between ITB and Technical University Delft, and we built together with Professor Gigahertz. Now I think he is a professor in Beijing. So in this, it is not clear here, but in this construction, we have all of the blocks that required for the working radar. So for example, we have frequency synthesizer, which is located in the left part of the figure. We have also a power divider, and then that one is IQ demodulator. And the upper part, we have power amplifier, and then in the lower part, we have low noise amplifier, etc. Maybe it's better to see the block diagram to see more clearly. Okay, next. Well, this is the setup in the experiment of GPR. We have this kind of laboratory, which is called GPR Test Range. In this test range, you have a box, a sandbox, a box, a large box, 3 by 3 by 3 meters, which is filled by dry sand. And the sand is special because we have to filter the sand, so we get only the good part of the sand, the small with small grains, and we put it in a box. And inside the box we put a loop antenna, and when we want to do an experiment with particular kind of object, something like ball or metallic ball, then you put the object inside the sand, and then we can activate this this test range to do the scanning. In this case, we don't use a dedicated step frequency radar. Instead, we use vector network analyzer operated as a GPR. And this test range is also equipped with 3 degree of freedom scanner. So the antenna can be brought around, can be moved around and positioned in 3-dimensional. So in this case, we scan this area from 300 kilohertz up to 3 gigahertz, which is the top capability of this vector network analyzer, and then controlled by a PC and collect the data and do the processing inside the PC. And this is the result. So if you collect all the data and do the inverse Fourier transform, then you get the top part of this curve. This is a perfect one, very clean, and you can see 2 reflections over there, which mean that there are 2 objects inside the test range. But if you want to make faster the data collection faster, you have to reduce the sample. And so the consequences is that if you make normal, you do the normal signal processing by using inverse Fourier transform, you get the second curve, and that means that the object now is less clearly seen, and there are so many noise clutters, and it's difficult to see that there are objects inside the sand. But after applying compressive sampling optimization, compressive sampling reconstruction, you will get the better result. Of course, if you only reduce it is a half, you get the bottom part of this curve. This is still so many samples. It is very, very good. And if we reduce the number of samples, then we can get we can still see the objects, but with less quality. And if you want to see, if you want to read the detail, we have published this result in IEEE Geoscience and Remote Sensing Letters, volume 7, number 4 in 2010. Well, what we see in the previous slide is an scan. We display only a particular point of scanning, and if you already move around the antenna, you can get the B scan. So we stack together all the scans and we get the image, and if display full scans, and we get the part A of the image, and we can see that there is a hyperbole. Yeah? Hyperbole means that we have a point reflector, and there are 2 of it in the top and the bottom. Yeah? So the top is more clearly seen because it's closer to the receiver, closer to the antenna. The bottom part is more difficult. When you want to speed up the sampling process, then you want to use compressive sampling. And again, we can see it is more clear when you apply the optimization algorithm, which is displayed in C and D. But if you directly constructed the image, you can get something like in figure B, which is not so clear. The reflection is now buried under the noise. So we Sometimes ago, about 15 years ago, we display our radar in an exhibition. So we built the wall. Yeah, the wall consists of one brick wall, but actually a thicker wall also works. So if there are a person behind the wall, we can detect him by using this radar, and you can see in the screen that there are objects that are hidden behind the wall. Okay, so let's go to the second part of the continuous wave radar with frequency modulated continuous wave GPR. Well, when we work with the step frequency, it is also in a time domain, but the frequency is scanned stepwisely. But in frequency modulated, it is scanned continuously from lower frequency F0 to the maximum frequency that they can, for example, FH, yeah, F higher frequency. And we can use simply the RAM to do this job. Yeah, RAM. I mean by the RAM is the modulation scheme. And you can see in the right part that the horizontal axis is time, vertical axis is frequency, and you can read here that when it is increased linearly, the waveform in the bottom part then become more dense. Yeah, become more dense which means that the frequency increasing from the lower frequency to higher frequency. This kind of waveform, we call it upchirp signal. And we can prove that there is a relationship between the range R and the bit frequency, which is R equal C multiplied by T multiplied by FB and divided by 2 bandwidth. And inside the radar, we can see the block diagram in the left part of this figure. It consists of VCO voltage control oscillator, and if we trigger the VCO with the linear waveform, sawtooth or a triangular signal, then it can transmit a chirp signal. And then after going to several blocks, including the power amplifier, and then transmitted with the antenna, receive again, and then we do the demodulation, then we got the bit signal. So basically, in the frequency modulated continuous wave radar, what we want is the bit signal. The bit signal is the difference between the transmitted frequency and the received frequency. Now, I will explain briefly about the design of a radar, an example. Yeah? So, because we actually built this radar, we can discuss later the detail. So, actually, our radar is based on a course in MIT, Massachusetts Institute of Technology, but we make some modification. In the MIT radar, we have it cannot work in real time. It cannot work in real time. So we modify the radar. We adopt the RF part, the radio frequency part, but we built our own block. Yeah. So for example, we have a baseband and IF module that we built based on existing microcontroller, which actually I think this kind of microcontroller, the Arduino. We simply use Arduino to build this radar, and we use PC or notebook for the processing and display module. So we have 3 block: processing display module, PPIF, RF module, and of course a pair of antenna. So in the RF block, we have VCO, attenuator, power amplifier, power splitter, LNA, mixer. Yeah. And all of this block, we bought it. Unfortunately, we have to import it from United States, but it's not so expensive. And we choose the block instead of discrete component because it is more simple to connect between the blocks. And of course, this RF block should be connected to other block, in this case is a BPIF module. So here's the pitchbend and IF block. In the pitchbend and IF block, we have a timing, sync, and clock signal generator. We have a RAM generator and RAM amplifier. And after going to the RF module, the signal will be sampled and we get the video amplifier. In the video amplifier, the signal is still analog, and we only take a particular spectrum of this signal. So we apply the low pass filter, and after conditioning circuit, we sample the pitch signal using analog to digital converter. And again, it is ADC which is available in the Arduino. And after sampling, then we send it to the PC using the data communication block. After getting the bit signal, which in this case is we packetize the bit signal, and we have the reason why we do the packetizing, because in each package of the signal, its data already synchronized. So we know the beginning and the end of the data, and it will actually consist of a correct range signal. And after getting the packetized bit signal, we can display directly to see whether the bit signal already correct or we have to do some adjustment. Sometimes the amplifier doesn't work properly, so the signal will be clipped, and it will be we will not get a good image. And if we already get the good bit signal, then we can do the IFFT. So after IFFT, we can get the time domain signal. We can display directly as a range signal or do further processing by using Doppler or aperture synthesis. So actually, some of my students doing aperture synthesis, where he bring around the radar by himself, yeah. So there is no vehicle, but bring around and then get the data and do the synthesis aperture processing. And of course, you can also do the Doppler processing. So for example, if you direct this radar to a moving object, car or other moving object, you can get the Doppler products which indicate the speed of the object being imaged. So here are some results. This is the implemented radar in a box. And well, this is interesting because by using, you can buy the component in Bandung in local shop, except the RF unit, RF unit, you have to import it from foreign company, but the PPF is quite affordable. And in this PPIF, you have simple component and microcontroller. As I told you, that it is consists of Arduino. 2 Arduinos should be employed here. Next. So this is the radar. When we put it together with display unit, display unit actually is a computer, it's a notebook, and we can see the detail in the next slide. So next. So in this figure, I use MATLAB to display the result. In the left upper part, it is a bit signal. So typically, pitch signal should be something like this. It is a sinusoid, and you remember in the previous equation that the frequency of the signal corresponds to range of the object. So if you have several objects, the pitch signal consists of several frequencies. And you can see here, instead of only one frequency, you have also the second and many other frequencies, and difficult to see. But if you do the Fourier transform and display in the right upper part of this figure, you can see the graph. Yeah, this is the peak indicates that there is an object located in particular range. Also, several other objects in other range. And you can display in other ways. For example, after getting several A scan, then you can stack together. You can get a P scan in the left bottom part of this figure, or you can display as a plane position indicator, such as in a normal radar in the right bottom part of this picture. In the fifth part, I will explain a little bit about the GPR application and data interpretation. So for the application, I have briefly reviewed in the previous slides. We can use it for roads, underground pipes, and cable inspection. And also, if there is a buried tank, but you don't know the specific location, you can use the GPR to locate and to figure out how large it is. Yeah? So we can use it here. Also, we can use it to detect the tunnels. And there is a specific reflection if we have a hollow pipes under the ground, and we can see in the screen. Also, we can use it for pre-text inspection. This is a typical image that we can obtain by from the ground penetrating radar, and sometimes it is called radargram. So, for example, in the left upper part of the figure, we see here several hyperbole, which means that there are several reflectors, several objects under the ground. And also we can see in the right part of this figure, we have a scan there. And an expert can see that, can interpret, can read from this radargram whether it is a concrete radar or even a sinkhole. And so I display here the difference between the 1 gigahertz and 2 gigahertz radar. So simply the difference is on the resolution. 2 gigahertz radar will have a higher resolution. You can see more detail of the object compared to 1 gigahertz. But again, the penetratability will be reduced for the higher frequency. Okay, so this is the last topic of our course. I introduce you the subsurface imaging by using magnetic field camera. So this is, we also built this camera by ourselves. When we start to build this camera, we don't know that other people already made it, but with a different purpose, different component, and a different dimension. So at that time, we think that we are the first that built this camera. And this is also a simple camera consisting of a microcontroller, which is, again, it is an Arduino, and several sensors, magnetometer sensor. They are breakouts of Arduino sensors, which is sometimes used for digital compass. Yeah, actually, we can read the strength of the magnetic field from the sensor. Okay, so let's see the block diagram. So we arrange the sensor into 4x4 array, and by a multiplexer, we can read one by one, and then by microcontroller shield, we can send it to microcontroller, and then by communication unit, it is sent to smartphone or a computer for further processing. So because our topic is subsurface, you can see that we can use this kind of camera for subsurface imaging. For example, if in the bottom part of the figure, we we put an object on top of two thick plus one less thick books, yeah. So in total, it is about, I think, about 15 or 20 centimeters. The camera in the bottom and can still detect or image, yeah, see the battery. The battery is a ferromagnetic material. Recently, we already enlarged the sensor, yeah. The array we use 320 sensors, magnetometers, and initially it is difficult to operate, to make this device work, because if you use only the component, what to say, if you don't use a microcontroller for its subarray, then it is very difficult to get the data. So we modify, then for each subarray we employ a slave microcontroller, so the collection of data now become more simple, and we can get a higher resolution image. And additionally, instead of only imaging a ferromagnetic object, it can also send image electricity. So in the house electricity, alternating current to 120 volt or 110 volt AC current can be imaged by using this device. And last, in the bottom part, you can see that some shape of the object can be clearly seen. So, for example, this right part of this image can show precisely the shape of the objects. Okay, I hope this will give some basic perception, basic understanding about subsurface imaging. So thank you for your kind attention.